Welcome to The Explainer. Today, we are diving into a paper that literally changed how we handle massive data sets, Google's MapReduce. It's a fantastic story about finding radical simplicity in the face of just overwhelming complexity. So, to get a sense of the scale we're talking about here, let's just start with a number. In the early 2000s, Google was processing over 20 petabytes of data. Yeah, you heard that right. 20 petabytes. Every single day. That is just a tidal wave of information. And this is the world that MapReduce was born into. This amount of data created an equally massive problem for Google's engineers. I mean, how on earth do you even begin to make sense of all that without getting completely crushed? You know, the authors of the paper, Dean and Ghemawat, they put it perfectly. They said, even a simple task was getting buried under this mountain of complex code just to make it run on thousands of machines. Every simple analysis turned into this huge, custom-built system. Okay, so let's really get into what this data nightmare actually looked like. Before MapReduce came along, every single big data job was this one-off, super fragile, and insanely time-consuming engineering project. So imagine you're an engineer, and your goal is simple. You just want to count how many times a word shows up across the entire web. Sounds easy, right? But back then, no way. You basically had to become an expert in distributed systems overnight. You had to manually figure out how to split the work, send it to thousands of machines, and, this is the really hard part, figure out what to do when some of those machines inevitably fail. Your simple goal was just buried. So as a reaction to all of this complexity, the authors had this brilliant insight. They were inspired by some ideas from functional programming, and they realized, wait a minute, almost all of our massive computations can be boiled down to just two core functions. The first one is called map, and you can think of this as the divide and conquer part of the operation. It takes a huge, scary problem and just breaks it into thousands of tiny, manageable pieces. It tells each computer, hey you, just worry about this one little document. Pull out the interesting bits, and we'll deal with it later. And the key is, this happens on all the machines at the exact same time. Okay, so that's map. The second part is reduce. And if map is divide and conquer, then reduce is the gather and summarize step. It takes all those little bits of information from the map phase, like, say, every time the word cat was found, and it brings them all together to give you one final, clean answer. And the classic word count example makes this just crystal clear. It's so elegant. So the map function skims through documents, and for every word it finds, it just spits out a little pair, the word and the number 1. That's it. Then, and this is the magic part, the system itself handles this huge, messy step in the middle called shuffle and sort. It automatically groups all the identical words together. And then, the reduced function has the easy job. It just has to sum up the ones for each word. The programmer writes two tiny, simple functions, and the system handles all the massive, mind-bending complexity. So you get the idea. Map and reduce. Simple, right? But the real genius is how this simple idea gets executed across an entire army of computers. And that brings us to the system's architecture, which, honestly, is where the magic really happens. This whole thing, it's like a perfectly choreographed ballet, but with computers. It all starts when your input data gets split into these manageable chunks. Then you have a master node. Think of it like a general, and it starts assigning map tasks to its army of worker machines. Each worker chugs away on its little piece and stores the results locally. Once that's done, the master starts handing out reduce tasks. These reduce workers then go and pull the data they need from all the map workers, do the final calculation, and write the output. And the best part? The programmer who wrote the code sees absolutely none of this. It just works. But okay, that all sounds great in a perfect world. What happens when one of those thousands of computers just dies, right in the middle of a job? Because in a cluster that big, failure isn't some rare event. It happens all the time. And this is really the secret sauce. MapReduce wasn't just built for speed, it was built for survival. It was designed from the ground up with the very real expectation that, yeah, machines are going to fail, networks are going to get flaky, and things are absolutely going to go wrong. And the solution is it's beautifully simple. The master is constantly pinging the workers. Hey, you still there? If one goes silent, the master just declares it dead and reassigns its talk to another machine. And get this, the paper has this incredible story where during one huge drop, 80 machines were taken offline from maintenance at the same time. And the MapReduce job, it just kept on chugging along and finished without a problem. It's all completely automatic. Insane.
But it's not always about machines completely failing. What about the ones that just slow down? The paper found that dealing with these stragglers was absolutely critical. In one large sorting job, when they turned off a feature designed to combat them, the whole job took 44% longer. That's a huge difference.
So yeah, it didn't just handle total failure. It also handled this really sneaky problem they called stragglers, machines that are technically working but are just running super slow for some reason. So near the end of a job, if a few tasks are holding everything up, the master proactively launches backup copies of those slow tasks on other machines. It's a race. Whichever one finishes first wins. This one simple trick made a massive difference in cutting down the total job time. Okay, so we have this new system. It's simple, it's robust, it handles failure. So what? What was the actual result of this new abstraction? Well, to put it simply, it completely revolutionized how Google worked with data. The adoption inside Google was, well, it was explosive. Look at these numbers. In just 3 years, the number of MapReduce jobs they were running grew by almost 100 times. It went from thousands to millions of jobs every single month. It basically became the default way to do any kind of data processing. And this is maybe even more telling. It wasn't just the same jobs running over and over. The number of unique MapReduce programs just exploded from 0 to 4,000 in 3 years. What this really means is that tons of programmers who had zero experience with distributed computing could now tap into the power of the entire cluster. It was a game changer. But if you want the ultimate proof of how powerful this was, look no further than Google's core web indexing system. One super complex component shrank from 3,800 lines of fragile C++ to just 700 lines of simple MapReduce code. And listen, this wasn't just about writing less code. It meant that a change that used to take months could now be done in days, which just massively accelerated the pace of innovation at Google. And this quote from the paper it nails it. It really summarizes the whole thing. It wasn't just about technical performance. It was about empowering people. It democratized large-scale computing for an entire generation of programmers and data scientists. By hiding all that insane complexity behind a really simple, restrictive interface, MapReduce didn't just solve a technical problem, it unlocked human potential. And it leaves you with this big question. Where is the next great simplification going to come from? What complex field is just waiting for its own elegant abstraction?